Okay, in this case, we are going to work out the tangential speed, angular speed, and period of revolution of celestial bodies like planets and satellites. So, in this case, we are going to work out a specific case in which the body about which another body is revolving is massive compared to the revolving body. Or you can just write ball M, which stands for the body at the center, is much greater than the body which is revolving around the body at the center. And obviously, we assume that the body moves in a near circular orbit. Assumption is that it's a circular orbit. The body moves in a circular orbit. Then we can apply the concepts of centripetal force and gravitational force. This is the basic idea. Now let us try a configuration here. Here we have a star, for example, of mass m. This is a star of mass m. And of about that star, you have a planet revolving in near circular orbit. I'm sorry, it doesn't look very nice, so I'll just do it again. Stop. It's a little bit. Okay, here we go. So you can see this is a star. And this is the center of mass of the star, which is much heavier compared to the mass of the planet, which is revolving around the star. So here we have a planet, a tiny planet for that matter. And this is the planet. All right. The mass of the star is small letter m we represent, and the mass of the planet we represent with small letter, and the radius of the orbit r. So the first attempt is to make an equation for the tangential speed. So this is the tangential velocity. Here we have the tangential velocity. Just put an arrow. Tangential velocity is represented by small letter v with a vector sign. Now let's try to work out the magnitude of the tangential speed. For that, let us consider the idea for the planet to move around the star. The centripetal force is provided by the gravitational force between the star and the planet. So we may write FCP is equal to FG. FCP stands for the centripetal force and FG stands for the gravitational force. So FCP, we can write mv square over r, where v is the tangential speed of the planet, and this must be equal to g, the gravitational force, gmm over r square. Now you must remember that the mass of the star is huge compared to the mass of the planet for these equations to be valid. Because the center of mass of the system we assume very close to the center of mass of the star. That's a basic idea. Now we resolve this equation. Let's solve it. M and M get cancels out, and R and one of the R's in cancels out, and you will get the expression tangential speed square of the tangential speed is equal to G M over R, or the tangential speed V is equal to under root G M, that is the mass of the star, R is the orbital radius. This is the first equation we get. The tangential speed is given by, doesn't look nice, let's put it a little bit lower. Here we go. All right, that's the first equation we get. We can also get the angular speed. Let's try the angular speed now. Same equations. So let's write it as, use a different color. Right. Okay. Take it as B, angular speed. We'll try to work out the angular speed in this case. Angular speed. It's usually represented by the letter omega. So in this case, we can again write the same relationship. FCP is equal to FG, but here FCP, instead of writing mv square over r, we'll write mr omega squared. mr omega squared is equal to G M over r square. Now let us simplify this equation. If you simplify, omega r goes down here to the denominator, turns it to r cube, small m and small m get cancelled out. You will get the omega value, angular speed. In this case, you will get the angular speed, angular omega is equal to under root G M over r cube. So that's the second equation we can get. Now we can another equation. That is the period of revolution. Let's try the period of revolution now. So C period of revolution, usually represented by the letter bold T. So this we can work out using the relationship. Period of revolution T is equals to 2 pi over omega, or you can write T square is equal to 4 pi squared over omega squared. Omega squared will be gm over r cubed. So this is equals to 4 pi squared over, right? Oh, funny. We can write it as G M over r cube. Now we simplify this. R cube will go to the top. Gm will stay in the denominator. You will get the relationship. T square is equal to 4 pi square over Gm times r cube. So often we say that, r cube. R is the orbital radius. So we can just write Square of the period is proportional to the cube of the orbital radius. This is usually called the Kepler's law, Kepler's third law. That is known as Kepler's third law, because this is an observation made by Kepler long before we could theoretically work out these relationships. So let's put all the relationships together.